Okay, so let me share. So as we have seen that the definition of the Markov chain is that if xn is equal to I is basically the process is in state I at time or step n, then the probability that the future given the present and the past, this does not depend on the past basically. So that is the definition. So that means this is some kind of dependence is there here. Okay, so that is the thing here. So but the dependence is just on the previous, okay, not on the all the values. So now we want to find we have started with an example that xn is a discrete time Markov chain with state space s is 1 2 3 and tpm is given to us. The pmf of the initial state distribution is given to us. Then we want to find what is the probability x2 is equal to 3, x0 is equal to 2 is x0 is equal to 1 2 3 is given to us. Okay, and we want to find this x2 is equal to 3. So last time we have done a result that our E n, the probability mass function of step xn is equal to probability mass function of step xn minus 1 into the TPM. So to mute yourself. Okay, now therefore let us first of that means first of all we will find out what is P2 and the elements here will be P12 P22 in this example, P32, and we need basically this value. This is the probability x2 is equal to 3. So but we know that Pn is equal to Pn minus 1 into the TPM. That is given to us. So first of all, let us find out the probability mass function of x1, which is P1, which is P0 into P. P0 is basically for step x0. Okay, for step x0 it is given to us 0.7, 0.2, 0.1. Therefore this is 0.7, 0.2, 0.1 into the TPM is given to us, that is this value 0.1, 0.5, 0.4. So 0.1, 0.5, 0.4, 0.6, 0.2 and 0.2, 0.3, 0.4, 0.3. So therefore after solving this we will get 0.22, that means 0.7 into 0.1 plus 0.2 into 0.6 plus 0.1 into 0.3, that is 0.22. Next value is 0.7 into 0.5, 0.2 into 0.2, 0.1 into 0.4, that value. So that is equal to 0.43. And next value is 0.35. This is the probability mass function of x1. For step x2, the probability mass function is P2, which is P1 into P. So P1 is 0.22, 0.43, 0.35 into the TPM 0.1, 0.5, 0.4, 0.6, 0.2, 0.2, 0.3, 0.4, 0.3. So therefore this will be 0.385, 0.336, 0.279. So, but we need this value basically, which is nothing but probability that x2 is equal to 3, which is P 32, which is 0.279. So this is the solution for this. Now, let us now start with the classification of states. So we have Xn is a discrete time Markov chain with the state space as 0, 1, 2, and so on. So let us say that I, J are states. So we say that state J is accessible from I. State I, in notation we can write this thing that your state J is accessible from I if Pijn is positive for some n, where Pij what? Pij is basically nothing but the probability that x n is equal to j given x naught is equal to I. This is the ijth element of n step TPM. Okay, so for some n, that means for some n it happens. If this happens, I and j communicate if we say state I and j communicate with each other if your j is accessible from I and I is accessible from j. If this happens, then we say that they basically communicate. So it is easy to show that I and j communicate, j and k communicate. This implies that I and k also communicate. I, j, k are states. Okay. So solution is easy because your I and j communicate. So therefore from I to j in some step n we can go. For some n there exist n and m such that p jk m is positive. So now pik m plus n. So now you have done the Chapman-Kolmogorov equations. From there, there exists some state L such that we can go from I to L in n steps and L to k in m steps. So therefore, this quantity is greater than equal to Pij n Pjk m. But from here, because it is given, so this is this. Okay. So now if j is accessible from I, k is accessible from j, then I is accessible from k. Similarly, other part you can do that k is also accessible from I. So therefore, similarly you can do that I is accessible from k. So therefore, this proof will go on. So proof will be complete basically in this fashion. So therefore, this is the result. Okay, so from here, what you have done, I is this one, j is this. So therefore, your k is accessible from I. Similarly, your I is accessible from. So therefore, this happens. Okay, any question here?
So this property is only for DTMC, right?
Yeah, because we are now talking about the discrete time Markov chain. So for others, whatever you define for that, you have to verify those. So for this is for basically discrete, because we are now doing the discrete time Markov chain only. Yeah.
Okay, sir.
So now Xn Markov chain is said to be discrete time. Markov chain is said to be irreducible or connectable if every state communicate with every other state. Otherwise, it is said to be, it is reducible. So it is connectable or irreducible if every state can communicate with every other possible states. Otherwise, it is said to be reducible or not connectable. So, for example, consider a discrete time Markov chain with having TPM as states are 0, 1, 2. This is 1 by 2, 1 by 2, 0, 1 by 2, 1 by 4, 1 by 4, 0, 1 by 3, 2 by 3. So you can see here that 0, 1, 2 from 0 to 0 we can go with probability half. From 0 to 1, we can go with probability half. From 1 to 0, with probability half. From 1 to 1, with probability 1 by 4. 1 to 2, with probability 1 by 4. 2 to 1, with probability 1 by 3. 2 to 2, with probability 2 by 3. So you can easily see here that from 0 to 1 we can go, because path is there, and 1 to 0 we can come back. So 0 and 1 are basically communicate with each other. Similarly, 1 to 2 you can go, and 2 to 1, 2 to 1 you can come back. So 1 and 2 are also communicate with each other. 0 1 communicate, 1 2 communicate, 0 and 2 also communicate. So therefore all the states, what are the states here? 0 1 2 in this discrete time Markov chain, because all states communicate with each other. So therefore Markov chain is irreducible or connectable. So Xn is irreducible or connectable. Okay, so now period of state. I, we can denote this by di. So period of state I is the greatest common divisor of positive integer n such that PIIN is greater than 0. Okay. If PIIN is equal to 0 for all n greater than equal to 1, we define period of state I to be 0. So let us take this previous example. So here for state 0, we want to find period. So now this is the greatest common divisor such that P 0 n is positive. So 0 to 0 in one step we can go. Yes, half with probability half. In two steps, yes, also from I can remain in 0 and then remain in 0, or I can go to 1 then come back. So probability is there, half into half plus half into half. So that is also possible. 2 GCD of 2, then 3 it is possible, and so on. So greatest common divisor is 1 here. So similarly, from for 1 also it is state 1 also it is coming out to be 1. State 2 is also it is coming out to be 1. So therefore period of state 0, 1 and 2 here are 1. If period is 1, then that state is either said to be has period all state has, in this example, period 1 or period 1 is also called aperiodic. Okay. Now let us take another example.
Could you please explain this again?
Yeah, so I'm saying that for, let us say that I want to find out for state 1, the period. So I have to take the greatest common divisor such that for all the value of n, such that it is from 1 to 1. What is P11n? P11n is the probability that xn is equal to, yeah, so that means your, yes, so x, your, yeah, in n steps, p xn is 1 given x naught is 1. Okay, that means in n step, this should be positive. Okay, for each value of n, I will collect. So whether in one step it is possible, if I take n is equal to 1, from 1 to 1, I can move in one step. Yes, with probability 1 by 4. So this is GCD of 1, comma. Whether in two step it is possible. Yes, I will remain in 1 and then remain in 1, or I can go to 2, then 2 to 1 I will come back, or I can go to 0 or I can come back. So probability is there, with positive probability is there. So that means 2. Similarly, in 3 steps also it is possible, and so on. So greatest common divisor of this is 1. So therefore, is it clear now?
Yes, sir.
Now let us take another example where period is 2. So let us take the xn is discrete time Markov chain having the TPM 0, 1, 1, 0. States are 0 and 1. So 0, 1, these are
Excuse me,
the
sir.
states. Yes.
So can you give an example of the second part when PII is equal to 0?
Yeah, I'm giving that. Okay. Just wait. So let us say that states are here 0, 1. So from 0 to 1, we can go with probability 1, and 1 to 0 we can come back. So what is the period of state 0? GCD of, so in one step it is not possible, in 2 steps we can come back, in 4 steps we can come back, 6 steps we can come back. So 2 here. Similarly, you can easily see that period of state 1 is also 2. So period here is 2. Period of state 0 and 1 are 2 here. Now, okay, so some examples you are asking where, yeah, period is 0. So yeah, so I can define like this, that states are like this. I have -2, -1, 0, 1, 2, -2, -1, 0, 1, 2. Okay, so these are the states. Now from 0 to -2 to -1 I can go. Then from -1 to 0 I can go. And so on. Okay, so in this fashion, that means -2, -1, 0, 1, 2. So 1, 1, 1, 1. Okay, so for example, I want to find what is P00n. how many steps I will take, I cannot come back. Okay, because if I leave that state, I cannot come back. So here clearly the period of state, any state you take, that will be 0. Is it okay?
Yes, sir.
Okay, now for state I, so Xn here, same thing is there. Xn is a discrete time Markov chain. Having TPM, and let us say I belongs to the state space. So now we define F I n or FIN is the recurrence time probability. Okay, you take FIN. Okay, so as the recurrence time probability. What is the meaning of that? That means probability that starting with state I, you visit state I in n steps. In between you cannot visit state I, where k is 1, 2, and -1. So this is the probability of first visit to state I in n transitions or steps starting from state I. This is known as the recurrence time probability. Sometimes it is denoted as FIN also. Okay. So FII0 is 1. And we define, it is clear FII0 is 1. Probability of ever visit to state I, FII or FI, this is FI1 plus FI2 plus FI3 plus so on. So what is this? This is probability of ever visit to state I, because Fi is the probability of ever visit to state I. Ever visiting state I, FII or FI. So if, because this is these probabilities visiting first time, either in 1 step or 2 steps or 3 steps and so on. Okay, so if Fi is 1, return to state I is certain. That means return to state I is certain starting from state I. Then state I is, if FII or FI is 1, then state I is called recurrent state. If return to state I is certain, then state I is called recurrent state. If Fi is less than 1, then return to state I is uncertain. Then state I is called transient state. Okay. So these are the definitions of recurrent state. Recurrent means return to state I is certain. That is Fi is 1. Fi is basically summation of this. Fi1, Fi2 and Fi so on. That means Fin, n is from 1 to infinity. So this is the definition of if Fi is 1, then I is recurrent state. If Fi is less than 1, then I is transient state. Let us give equivalent definition. Some other definition, let us give equivalent definition to this. So let we define In as 1 if xn is equal to I, 0 if xn is not equal to I, then summation In, n is from 1 to infinity, is the number of time periods the process is in state I. State I. Now, expected number of time periods the process in state I, given that we start in state I. Okay. So, expected number of time period the process is in state I if we start from state I. So this can be written as, because you know that expectation will go inside. This will be expectation of In given x naught is equal to I. Now expectation of this is nothing but 1 into probability x n is equal to I given x naught is equal to I plus 0 times probability xn is not equal to I given x naught is equal to I, using this. Now that means this is nothing but summation n is from 1 to infinity probability xn is equal to I given x naught is equal to I, but this is nothing but summation n is from 1 to infinity p I n. Now you know that I is recurrent if return to state I is certain. Now once it return to state I, then because it is a recurrent state, again it will return to state I. How many times it will return? Infinitely often. So therefore number of time periods if I is recurrent state, then return to state I is certain. So therefore expected number of time periods the process is in state I diverges, and if I is transient return to state I is uncertain. Then that means this expected number of time periods the process is in state I starting from state I converges. So that is also equivalent definition. So we can say that if Fi is 1 or Fi is less than 1. So these are the equivalent definition for recurrent or transient state. Either you can check either of them. Where Fi is different from PII. Okay, it should be noted that Fi is probability of first visit to state I, whereas PII is the conditional probability that xn is equal to I given x naught is equal to I. And these are also the conditional probabilities, but probability of first visit to state I, probability of ever visit to state I, first visit plus second visit plus third visit plus so on. Okay. Okay, now if I is recurrent, we define Mi as mean recurrence time, which is summation n f I n. This is called the mean recurrence time. Expected number of the time the process return to state I. That means expected time the process return to state I. Time does not mean here exactly time, means transition, steps, etc.
Sir,
Yes.
sir, expected time the process returned to state I for the first time. Sir,
No, not for the first time. Expected time, expected periods basically. Expected, we can say time here means transitions, etc. Transition steps, because time doesn't mean exactly time here.
sir, FIN means that it should return to I in the nth step and not before.
Nth step. Yeah, nth step basically. FIN means probability of first visit to state I in n transitions, starting from state I.
So the mean value should also be the mean value of the first visit to ith step.
Okay, yeah. So means x, yeah. So that means expected step. In how many steps basically you are expecting that basically.
Okay, sir.
Time doesn't mean exact time, means transitions or steps basically. Yeah, that is okay. Yeah. So if Mi is diverges, then I is called null recurrent. If Mi mean recurrence time converges, then I is called non-null recurrent. Or positive recurrent. Here sometimes this is denoted as MII also. Okay, so okay, let us take some example to understand better. So let us consider a discrete time Markov chain having states 0, 1, 2, 3, 4 and TPM as half, half, 0, 0, 0, half, half, 0, 0, 0, 0, 0, half, half, 0, 0, 0, half, half, 0, 1 by 4, 1 by 4, 0, 0, 1 by 2. This is the TPM and states are 0, 1, 2, 3. So initial we can write here 1, 2, 3, 4, 0, 1, 2, 3, 4. So this is the TPM. Now, first of all, let us classify the states basically. So from 0 to 1, 2, 3, 4. So from 0 to 0 we can go. From 0 to 1 we can go. From 1 to 0. Then 1 to 1 we can half, 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 and 1 to 1 we can go half. Then 2 to 2 we can go half. Then 2 to 3 we can go half. 3 to 2, 3 to 3. Then 4 to 0, 1 by 4. 4 to 1, 1 by 4. And 4 to 4. Okay, now because states are finite here, state space is finite. So first of all, you note down here that from 0 to 1 we can go and 1 to 0 we can go. Okay, so 0 and 1 communicate. Similarly, 2 and 3 clearly communicate, but from 4 we can go to 1, but from 1 we cannot come back to 4. Similarly, 4 to 0 we can go, but from 0 and 1 we cannot come back to 4. So 4 is basically separate. So 0, 1, 2, 3 and 4, these are classes or equivalence classes. So if any 0, 1, 0 is recurrent, 1 will be recurrent. If 0 is transient, 1 will be transient. If 2 is recurrent, 3 will be recurrent. 3 is recurrent, then 2 will be recurrent, like that. Okay, because they are in same class. First of all, whether Markov chain is reducible or irreducible, whether all states communicate with each other.
All states do not communicate.
Yeah, do not communicate. So that means this is not connectable or irreducible. This is reducible Markov chain. So this is reducible Markov chain, first of all. After that, first of all, by the diagram itself, because recurrent means that you will visit state infinitely often. That's why we have written this infinite, because you will visit state infinite often. Return to state I is certain, starting from state I. So if you are in state 0, again you will visit state 0 again and again and again, whether you can go to state 1 sometimes, but again and again you will visit state 0. So state 0 is basically a recurrent state. From the diagram itself we can say, if 0 is recurrent, 1 is also recurrent. So because they are in same class, so therefore this class is basically recurrent. Similarly, 2 and 3, if you are in 2, given that you are in 2, you will visit state 2 again and again infinitely often. So therefore 2 and 3 are also recurrent. 4, if you are in state 4, you may be in state 4 for finite time. Finite may be large, but at the last either you will be in state 0 or 1. So therefore you cannot visit state 4 infinitely often. You cannot visit. So therefore state 4 is basically transient state. Now this is using basically the argument or basically seeing the diagram, but you can prove mathematically also. At least once we have to see that this happens. So let us see for state 0. So what we have to find out? We have to find out f0 basically. F0 should be 1. So f0 is f01 plus f02 plus f03 plus so on. So f01 means starting from state 0, you will visit state 0 for the first time. In between, you cannot visit state 0. That is the meaning. Okay, that is FIN basically. FIN means return to first visit to state I in n transition starting from state I. In between, you cannot visit. So it is saying that in one step, you have to return to state 0. In between, you cannot visit. So one step is half basically. From 0 to 0, you can visit in one step half. Plus in 2 steps, you have to visit, but in between, you cannot visit. Okay, so you cannot stay in 0 because you cannot visit in between. In 2 steps, you have to visit state 0, but in between, you cannot be in state 0. So you have to go from 0 to 1 and then 1 to 0. Half into half. That is the only possibility. No other possibilities. If some other possibility is there, then you have to add that. So that will be half into half. Plus f03. In 3 steps, you have to come back. In between, you cannot visit. So 0 to 1, then stay in 1, then come back. No other possibilities there where you don't have to visit in between 0. So half into half into half. 0 to 1, then stay in 1, then come back. Half into half into half. So that is the only possibility in this case. Okay, so therefore this is half 1 plus half plus 1 by 4 plus so on. So therefore this is 1 into 1 divided by 1 minus half, that is V1. So that is the basically f0 is 1. So therefore by definition, if f0 is 1, 0 is basically recurrent. State 0 is recurrent state. Similarly, state 1 will be recurrent. Okay, so if period of state 0 is 1 here, period of 0 is 1, period of state 1 will be also 1 aperiodic. Also, you can easily see that this is aperiodic also. Similarly, state 2, period of state 2 is also GCD of PII P22 N. N is basically GCD of 1, 2, 3 and so on. So therefore, this is also aperiodic. Okay, so now, so this is the case here. Now, let us prove this thing. What we have shown is basically if state 0 is recurrent, state 1 will be also be recurrent. They are communicating with each other. Okay, so which are in one class, they are basically, if they are recurrent, other will be recurrent. If other is recurrent, transient, other will also be transient. So let us show this. Let us say that I and J communicate. I is recurrent, implies that state J is recurrent. We want to show this. Now, because it is given, so that means there exist N and M such that P I J N is positive and P J I M is positive, that is I and J communicate, and I is recurrent, that means P I new is from 1 to infinity, diverges. This is given to us. Now we want to show that J is recurrent. So that means let us take PJJ M plus N plus nu by the Chapman-Kolmogorov equation. This is P J I N P I nu P I J M. Now take summation on both sides, summation over nu P J J M plus N plus nu is greater than equal to P J I N P I J M summation over nu P I nu, but we know that this diverges. Other side also diverges. So therefore, this implies that summation nu Pj summation n P I J J N also diverges. If this diverges, that means J is recurrent state by the definition. So we have shown that if two states communicate, one is recurrent, other will be recurrent. Okay, so let us stop here. So next time we will show that if if two states communicate, one is transient, other will be transient, and some other properties we will show. Any question till now?
Sir,
Yes.
so we are dropping M plus N because it is finite from the left hand side.
It doesn't matter now because this summation is there. It is going towards very large value basically.
Yes, sir.
So that's why if that will be diverges, other will also diverge. Okay, let us stop here. So any other question is there?